So, it is important to keep in mind that when we specify a group, we must specify a group operation. Okay. So, let us look at a couple of more examples of groups before we study properties of this. So, I want to generalize the definition of S3 that we considered. So, recall that S3 was the set of bijections of the set 1, 2, 3, and S3 under composition is a group. Okay. We can generalize this, there is nothing special about 3. So, now I define Sn for any positive integer n So, n is a positive integer. Sn is the by definition the set of bijections of the set 1, 2, 3 up to n. And recall the exercise I gave in the first video. If you compose two bijections, you get another bijection. So, that exercise tells us that Sn is closed under composition, just like S3 was closed under composition. So, Sn is closed under composition. It has an identity element, namely the identity function. Remember, this is the function which sends 1 to 1, 1 to 1, 2 to 2, 3 to 3 and so on, n to n. It is the identity function, because when you compose any function with this function, you get that function back. Similarly, every element okay, this requires a little bit of thinking, but we can prove this, as every element has an inverse, meaning if you give me any bijection of Sn, there is another any bijection of 1, 2, 3 up to n, you can just construct another bijection such that composition gives you identity. For example, if one bijection sends 1 to 2, you can simply send 2 to 1 under a new bijection. So, the composition will send 1 to 1. So, every element has an inverse, and composition as always is associative. So, in other words, Sn under composition is a group. Okay, Sn is a group under composition. We are going to spend in one of the future weeks a lot of time on understanding the group Sn. It is called, it has a name, it is one of the important groups in group theory. It is called the symmetric group on n letters. It is called the symmetric group on n letters, letters being 1, 2, 3 up to n. So, it is a group on those letters. So, it is called the symmetric group on n letters, and it is, as I said, very important group in the theory of abstract groups, and we will study this later in more detail. Okay. So, one more example that I want to discuss. Okay. So, just to recap a little bit, we have several examples of groups now. We have groups of numbers like z, q, r, c, positive rationals, non-zero rationals, positive reals, non-zero reals, non-zero complexes under either multiplication or addition are groups. Similarly, we have symmetric groups. We studied S3 in the previous video in detail. Now, I defined Sn in general, that is a group. We also talked about group of rotations of an equilateral triangle. And another group that I want to discuss, this is also an important group for us. We will refer to this again in future. Let us look at the I am going to give you a set of complex numbers. So, fix a positive integer n. Okay, so, n is a positive integer, and I am going to define a complex number theta n to be cosine plus I sin 2 pi by n. Okay, so, complex numbers are of the form a plus I b, where a and b are real numbers. So, here I am taking cosine 2 pi by n plus I times sin 2 pi by n. So, if you know a little bit about complex numbers, it is not important in general for the course, but in this example you need to know this. If you have a complex number of this type, when you take the nth power of this, in other words I am taking cosine 2 pi by n plus I sin 2 pi by n. So, I am taking the whole power n. This, by the properties of complex numbers, simply happens to be cosine 2 pi plus I sin 2 pi. So, what happens is you multiply n with this 2 pi by n with this 2 pi by n, but cosine 2 pi is 1, sin 2 pi is 0. So, this is 1. Okay, so, theta n power n is 1. So, we say that theta n is a primitive nth root of unity. Okay, so, it is an nth root of unity because theta n power n is 1, and it is primitive because theta n power m is not equal to 1 if m is a positive number less than n. So, it is not an mth root of 1 for m less than n, it is the smallest positive integer such that theta, a power of theta is 1 is n. Okay, so, this is what makes it primitive. Again, this is if you do not know complex numbers, you can disregard this example, but now let me define g to be 1 theta n squared. Okay, here powers are, so I am here the operation is simply multiplication of complex numbers. Okay, so, I am only when I write theta n squared, I mean theta n times theta n. Theta n power n minus 1 is theta n multiplied with itself n minus 1 times. And remember, when I do theta n power n, I get 1 back. So, this is what I get. So, this I claim under multiplication is a group. Let us spend 2 minutes on why this is the case. Why is it a group? Because is it closed under multiplication? If I multiply theta, what are the elements of this? Theta n power I is an element times theta n power j, that is another element. What is theta n power I times theta n power j? It is theta n power I plus j, but because theta n power n is 1, theta n time power I plus j will be equal to one of these, because I mean it is easiest if I say by example. If theta n power n minus 1 times theta n squared is theta n times 2 n, sorry, n plus 1, but this is theta n times n power n times theta n, which is theta n. Okay, so this is again in the group in the set G. So it is closed on AS, identity yes, 1 is there, right, that is identity, inverse. So, I am asking again, remember what is a group, it is closed, binary operation is closed, that we checked here, quickly checked, identity is there, yes, multiplication is certainly associative. So, again that we do not need to check separately. Is there an inverse? Yes, again, because what is the inverse of theta n power I? That is simply theta n power n minus I, because if I do theta n power I times theta n power n minus I get theta n power n, which is 1. Okay. So, inverse also exists. So, this is a group. Okay. So, this group G, the group G being what I defined earlier in the previous page, and X is the multiplication, is a group. This cross is the multiplication, is a group. It is called, it is an important group, it is called the group of nth roots of unity. It consists of nth roots of unity. Remember that every element of this group is an nth root of unity, because if you do theta n power I power n, then this is certainly equal to theta n power n power I, because this is just I n and I can pull out I, and this is 1 power I and this is 1. So, everything here is an nth root of unity, however, everything here is not a primitive nth root of unity. So, it is called the group of nth roots of unity. A familiar example that you all know is if you take n equal to 4. Remember, theta 4 is cosine 2 pi by 4 plus I sine 2 pi by 4. Okay. So, my notation I realize now is a bit confusing. Here I refers to the square root of minus 1. Here I is just an index. So, what is cosine 2 pi by 4? That is just 0, that is cosine pi by 2. So, this is simply I. So, theta 4 is the primitive fourth root of unity, which is I. So, what is G? So, I should really call these groups G n's. So, I should maybe call this G n. So, G 4 is 1 theta 4, which is I, theta 4 squared. What is I squared? I squared is minus 1, comma theta 4 cubed, which is minus I, and that is all. So, this is simply 1 I minus 1 minus I. So, this is the group of fourth roots of unity. And one more point that I will make, which is useful sometimes to keep in mind, is all the roots of unity for any n are on the unit circle. So, if you look at the unit circle, this is 1, that is a first root of unity, this is minus 1, you have I here and minus I here. In more general, you have cosine 2 pi by n plus I sine 2 pi by n, and that is this name, okay, and this angle is 2 pi by n. Okay. So, these are elements on the unit circle. So, this is another example. So, again in this video also I am basically trying to give you examples of groups. We have various groups now, we have groups of numbers, we have groups of bijections of a given set, and now I have a group of nth roots of unity. One more important example is the group groups of matrices. So, groups of matrices are good examples of matrices groups in future for us, and I am going to spend just a couple of minutes describing them, and then as and when needed we will discuss more of this. So, if you know what groups are matrices are, let us say you fix two positive integers m and n, and we consider m by n matrices. We have to specify where entries come from. So, let us just take R. So, these are matrices where entries are real numbers. Okay. So, the set, I think I called them m and so let us just take the notation is m by n R is the set of all m by n real matrices. Okay. So, these are, for example, this is m rows and n columns. So, we can, there is an addition here. Right. So, you can add matrices entry wise. So, m by n R is a group under addition. This is easy to check. For example, if you take let us say 2 by 3 matrices. So, you have A 1 1, A 1 2, A 1 3, A 2 1, A 2 2, A 2 3. You can always add 2 matrices B 1 1, B 1 2, B 1 3, B 2 1, B 2 2, B 2 3. There is no the fact that it is a matrix is irrelevant here, it is just a way of arranging certain real numbers. So, you just add them component wise. Okay. So, it is just the same. Okay. So, because addition under reals is a group, you can quickly check that this is also a group. The identity element, for example, will simply be 0 0 0 0 0 0. So, there is no surprise, this is simply several copies of R. So, that is not surprising. On the other hand, you can also ask matrices form a group under multiplication, that also you can ask. Because there is a way to multiply matrices. Immediately you have to impose certain restrictions, because you can't multiply a 2 by 3 matrix with a 2 by 3 matrix. You can't multiply, right. In order to multiply 2 matrices, the number of columns in the first one must equal the number of rows in the second one. So, restrict our attention to square matrices. Remember that in terms of the language that we are developing, multiplication is not a binary operation on the set of matrices if I do not specify that they are square matrices, because I cannot combine 2 by 3 matrices under multiplication, but now I overcome that difficulty by considering square matrices. Here at least we can multiply and we do get a binary operation. So, we do have a because any 2 square matrices can be multiplied to get another square matrix. However, this is not a group because not every matrix has an inverse. if you have studied matrix theory earlier, you will see that there are many matrices which do not admit inverses under multiplication. In order to do that, the matrix has to be what we call an invertible matrix. So, if you look at M n R to be all n by n matrices over R, if you do that, we agree, I hope, that M n R is not a group under multiplication of matrices. Because even though it is a binary operation, in other words multiplication is closed, not every matrix has an inverse. But if you look at, so the reason is, let me just write it here, because inverses do not exist in general. Okay. So, that is the reason why it is not a group, but we will restrict our set of matrices in order for inverses to exist. So, now define, it is usually denoted GLN R to be the set of invertible n by n matrices over R. Okay. So, we have artificially restricted our attention to only those which admit inverses. Then GLN R is a group. Okay. So, again this requires a small verification which I will leave for you to do. But I will just run through what you require to do. We need to check that multiplication is a binary operation. Certainly it is. If you multiply two invertible matrices, you do get another invertible matrix. Is there an identity element in this? Yes, there is, because the identity matrix is invertible. Are there inverses? Yes, because we have restricted our attention to only those matrices which admit inverses. So, every element in GLNR has, this is GLNR, every element in GLNR has an inverse, and matrix multiplication is associative, that you have studied in some matrix theory course. So, GLNR has all the required properties of a group. So, it is a group. Okay. This is an important group for us. So, I will end the video now, but to recall what we have done today in this video is, first we started with the definition of a group and then have seen a series of examples of groups which will be very important to understand in future when we study properties of groups. So, in my next video I am going to quickly recall all the groups that we have learned and then study some properties of groups.